Welcome back everyone. So in the last video we talked about the first derivative using Taylor series approximation. Now in this video we are going to talk about the backward difference form, forward difference form and the central difference form of second order derivative. And if you understand this methodology, then you will be able to calculate any order difference with any order error. So let us talk about second order derivative. We want to find out it using, first I am talking about forward difference formula. So I have this point xi, I have this xi plus 1, I have this xi plus 2. So if we are calculating the second order derivative, then we need 3 points. We can use more points as well if we want to enhance the accuracy. So I'll tell you the what is the error order of error, and if you use more points, then what will be the order of error. So if I calculate f of xi plus 1, that will be f of xi plus f prime xi xi minus x minus xi plus xi plus 1 minus xi f double prime xi upon factorial 2 xi plus 1 minus xi to the power 2. Now if I calculate f of xi plus 2, that will be nothing but f of xi plus 2 f prime, sorry, uh, this will be 2 f prime xi xi plus 1 minus xi, because this will be xi plus 2 minus xi, and that will be replaced by x, because this is delta x, this is delta x, plus f double prime xi upon factorial 2, and this will be 2 times, so this will become 4 times xi plus 1 minus xi to the power 2. Now let us focus on this, that so I am going to write down these two expressions in the next slide, and that is f of xi plus 1, that becomes f of xi plus f prime xi plus 1 minus xi to the power 1 plus f double prime xi upon factorial 2 xi plus 1 minus xi to the power 2 plus f triple prime xi upon factorial 3 xi plus 1 minus xi to the power 3. Similarly, xi plus 2 will become f of xi plus f prime xi 2 times xi plus 1 minus xi plus f double prime xi upon factorial 2 4 times xi plus 1 minus xi to the power 2 plus, let us say if I write down this order of x cube, and this is also order of x cube. Now this is my second equation and this is my first equation. Now if I do this thing, what I am doing is I am trying to subtract first equation minus from the second equation multiplied by 2. So what I am doing, I am multiplying the first equation with 2 and subtracting it with the second equation, and that will eventually lead to this will become what so what this will become, f of xi plus 2, f of xi plus 1, and then this will be, okay. Now I'm trying to modify this. Actually I don't want to cut this, xi, because I want to keep it, because if I uh, subtract this thing, uh, Okay, let us do this only. Let us not go into the details of f of xi plus 1. Let us do this only. So what this will give me? This will give me f of xi plus 2 minus 2 times f of xi plus 1 equal to minus f of xi. This thing will cancel out and this will become plus, if I multiply this with 2 and subtract, so this will become 2 times f double prime xi upon factorial 2 and xi plus 1 minus xi to the power 2 and this order of x cube. Now I am taking delta x as xi plus 1 minus xi. So this becomes, f double prime xi is equal to f of xi plus 2 minus 2 of f of xi plus 1 plus f of xi upon delta x square plus order of delta x square. Sorry, order of delta x, because delta x square will be divided. So my f double prime xi became f of xi plus 1 minus, sorry, f of xi plus 2 minus 2 f of xi plus 1 plus f of xi divided by delta x square plus order of delta x. This is forward difference second order derivative formula with first order accuracy. Now remember, this kind of formula will be applicable when we want to find out the gradient at this boundary, because there are no points towards this side, there are only forward points. So forward difference will be applied at the boundary. So if we want to use this double derivative at this particular boundary, then this will be my xi, there will be some xi plus 1, there we will have xi plus 2, and then we will apply this formula to calculate this double derivative at this particular boundary. Now let us understand the second order derivative. So, backward difference formula. For second order derivative. So what I have? I have this xi, I have this xi minus 1, I have this xi minus 2. So f of xi minus 1 will be nothing but f of xi minus delta x f prime xi, where delta x is xi minus xi minus 1 equal to xi minus 1 minus xi minus 2 plus delta x square upon factorial 2 f double prime xi minus delta x cube upon factorial 3 f triple prime xi. Similarly, if I write down the xi minus 2 thing, then it will be f of xi minus 2 delta x f prime xi plus 4 delta x square upon factorial 2 f double prime xi minus 8 delta x cube upon factorial 3 f triple prime xi. Now this thing I am expressing as order of delta x cube, and this is also I am expressing as order of delta x cube. Now if I do this, now what I want to do, second minus 2 times first, and that will give me f of xi plus 2 minus f2 f of xi minus 1 equal to f of x minus f of xi plus that will give me delta x square f double prime xi plus order of delta x. Now if I calculate the double derivative xi, that will be f of xi minus 2 f of xi minus 1 plus f of xi, and that is divided by delta x square plus order of delta x. So my backward difference formula becomes f double prime xi equal to f of xi minus 2 times f of xi minus 1 plus f of xi divided by delta x square plus order of delta x. Now remember, This is second order backward difference formula with first order accuracy. Now I want to do the central difference. For d2y over dx square or d2f over dx square. So in this I have this xi plus 1, xi minus 1. I will calculate f of xi plus 1, that will be given as f of xi plus delta x, f prime xi plus delta x square upon factorial 2, f double prime xi plus order of delta x cube, order of delta x cube. And this thing, let us write this down. This will become as delta x square upon factorial 3 f triple prime xi plus order of delta x की power 4. Now if I write down the xi minus 1, that will be equal to f of xi minus delta x f prime xi plus delta x square upon factorial 2 f double prime xi minus delta x cube, this is cube, delta x cube upon factorial 3 xi plus order of delta x की power 4. Now 1 plus 2, I am doing 1 plus 2. Now remember, if I do 1 plus 2, these things will add up, these things will add up, these things will cancel out. So this thing will cancel out and this thing will also cancel out. So that will essentially give me that f of xi plus 1 plus f of xi minus 1 equal to 2f of xi plus f double prime xi delta x square plus order of delta x की power 4. So what I got, f double prime xi equal to nothing but f of xi plus 1 minus 2f of xi plus f of xi minus 1 divided by delta x square, and order of error is delta x square. So if I write down the formula again, that is f double prime xi equal to f of xi plus 1 minus 2f of xi plus f of xi minus 1 divided by delta x square plus order of delta x square. This is central difference, second order derivative with second order accuracy. Now if I summarize, so I am writing d2f over dx square forward difference, then I will write backward difference, then I will write central difference. So the forward difference formula says that we have f of xi plus 2 minus 2 f of xi plus 1 plus f of xi divided by delta x square, and the error will be of delta x. The second, this thing says f of xi plus, f of xi minus, f of xi minus 2 plus f of xi minus 2f of xi minus 1 divided by delta x square, then error is of order of delta x. The central difference says that we have f of xi plus 1 minus 2f of xi plus f of xi minus 1 divided by delta x square, but here the accuracy is more, we have the order of accuracy as delta x square. Now I want to say that what we did, basically we tried to cancel out the lower order derivatives from the Taylor series expression to find out the double derivative and the first derivatives. Now if I want to improve the accuracy of the finite difference formula, then what I can do, I can take more number of points in the in the Taylor series, and then other than the desired derivative, I can cancel all the non-desired derivatives. So suppose if I want to calculate d2f over dx square and I take 5 points. So other than this d2f over dx square, whatever derivatives we have in these equations, we will try to cancel out those derivatives to enhance the accuracy of this finite difference formula. So I will cancel out df over dx. I will cancel out d3f over dx cube. I will cancel out d4f over dx4. So this way we can include more number of points to enhance the accuracy of the finite difference formulas. And this is very essential. This can be applied when we are making a solver. So this can be applied towards the center, this can be applied towards this boundary, this can be applied towards this left boundary. But what I want to say, if we mix the derivatives, so suppose at this particular boundary I am applying a backward difference that is having order of delta x, and at this particular boundary I am applying order forward difference that is having order of delta x, and in the central nodes I am applying the central difference square that is of order x square. So the overall formulation will have the lowest error. So the overall discretization of this domain is not of order of delta x square, it is of order of delta x. If I want to improve the this order, then I need to incorporate more points to enhance this order of delta x to order of delta x square. So that's what I mean, because in most of the cases the boundary application or the boundary finite difference formula for the boundary have the lower order of accuracy, so it basically reduces the accuracy of the overall solver. If we basically want to maintain the accuracy of the solver, then at the boundary nodes also we need to find out the finite difference formula with same accuracy. So that is one of the important point for the CFD people, those who do CFD. So in most of the cases they apply central difference in the central nodes, but at the boundary to calculate the first derivative they do not go for the finite difference formula with order of delta x square accuracy, they directly apply the formula with order of delta x. So first what they need to do, they need to find out the second order finite difference backward or forward formula with order of accuracy of delta x square, then they must apply that formula at the boundary. So this is very important in case of computational fluid dynamics if we want to do enhance the accuracy of the solver. Okay, so I hope I am clear and I have finished this Taylor series application to in finite difference methods. Thank you.